Hi, this is Mr. Mitchell with a video on gravity. When we speak of forces in motion, we cannot ignore one of the most influential forces in the universe, gravity. And for some reason, I wanted to put a picture of a little goat that seems to be defying gravity, but it's not. And I put some other pretty cool stuff, maybe. But anyway, you may recall that an attractive force called gravity affects all objects with mass. Now, you and I have mass, and we're not attracted to each other. We just don't have enough mass to be attracted to each other like Earth, Moon, and other outer space spheres have, because they really have a lot of mass, and you can get measurable gravity from those huge spheres out in space. Gravity is what pulls us and all falling objects toward Earth. And if you were on another planet, it would pull you toward there at a different rate of gravitational acceleration. But we'll talk about gravitational acceleration at the last slide of this video. So how does gravity influence motion? Well, it actually was Isaac Newton here who studied the motions of planets in the 1600s, and he came up with the principles of what we call the universal law of gravitation, or law of universal gravitation. The law of universal gravitation says that there are two factors that influence gravitational force. One factor is the size of the objects. And no, even sumo wrestlers, if they weigh 300 or 400 pounds, are not big enough. And the distance between the objects. So let's try to kind of talk about this. We have two objects that are the same size here. If we were to cut those objects in half, then the force, the gravitational force, would be half. However, it's not the same way as if you have a different distance between objects. The distance makes more of an influence because of this principle. If you have two of the same sized objects that are doubled in distance, the force reduces not by 2 like it did over here, but by 4. So you really decrease the gravitational pull the farther an object is away from each other. That is why when you have like the sun and the earth, the sun is much bigger than the earth here. However, the moon is more gravitationally attracted to the earth because how close it is. Even though the sun is way, way bigger, how close the moon is to the earth determines why it is revolving around the earth and not revolving around the sun like you would expect to because of its size. So there actually was kind of an interesting thing that determined another planet, and it has to do with the law of universal gravitation. When astronomers only knew that there were 7 planets, the motion of Uranus from the law of universal gravitation kind of disagreed slightly with what people observed. In other words, this planet Uranus here, the people who could see it from the telescopes, they expected it to move at a certain distance in a certain amount of time because of the law of universal gravitation. So it wasn't. And people were wondering, astronomers were wondering why that was, and some of the astronomers deducted that there must be a force from farther out that is influencing its revolution around the Earth. So a couple of astronomers actually deducted what the path of Neptune was around the sun before Neptune was actually discovered. And that's how Neptune was discovered, because if you could concentrate on the path that they thought it would be, then that's where they did in fact discover Neptune. So I thought that was pretty good use of the law of the I don't know why I'm having trouble with this law of universal gravitation. So gravitational force on an object is also called its weight. And yes, weight is a force. So when you're standing on the scales, there is a force that is bringing you toward Earth, and that's what is being measured, is the force that you're being brought toward Earth. If you were on a different planet, that force, that weight would be different. If you weigh 112 pounds here, you would not weigh 112 pounds on another planet, and I can't remember the last time I weighed 112 pounds. But anyway, there is a calculation for weight more than just standing on the scales. The calculation for weight looks a whole lot like another calculation we've had. We have weight equals mg, and that, yes, is the same function as force equals ma. Force equals mass times acceleration. Weight is a force. Mass is the same, and it's both in kilograms, and the g is the gravitational acceleration. So we are truly calculating force because we have the mass and we have the acceleration. So it's the same thing. Force was in newtons, weight is in newtons, mass is in kilograms, acceleration and gravitational acceleration are meters per second squared. Now you may say, weight is not in newtons, but yes, it is in newtons. About 4.4 newtons equals 1 pound, so it could be converted over. Here you see 9.8 meters per second squared equals g. That is the gravitational acceleration here on Earth. So if we happen to be on a different planet, you can see there's a chart as to what the gravitational acceleration would be there. Why is it not 9.8 everywhere in the universe? Well, it's because Earth does not have the other planets do not have the same mass as Earth. So it is 9.8 meters per second squared here because of the mass of the Earth. And you can see what it is here. Oh, we've got Pluto on this list. Where did Pluto come on this list? Pluto should not be on this list. It is not a planet. And you can see the squirrel over here is shocked that we even have Pluto on this planet. So on this list. Let's take a look at us solving something in W equals mg. You can see work is in newtons, just like force was, kilograms and meters per second squared. This squirrel, or a squirrel like it, weighs probably about 3.3 kilograms. So, or I would say its mass is about 3.3 kilograms. Let's find its weight. So it is as simple as plugging in 3.3 kilograms and 9.8 meters per second squared, because that's what you will, the gravitational acceleration on Earth, and it comes out to 32 newtons. Now, I said earlier that about 4.4 newtons equals 1 pound, so that if you do the calculations here, that puts this squirrel at about 7 or 8 pounds. So I hope you have learned a thing or two about gravity.